Hi, Mona Shore Sailors, 7th graders. This is Mrs. Cargill teaching you a study of surface area. And from your textbook, that is lesson 8-6. But before I teach you about surface area, I am wondering how you are all doing while at home for a few weeks. I know that I'm hearing from a few of you. You're sending me pictures about doing different things like even getting outside, bike riding or walking. A lot of you are reading books. Besides doing math, you're playing games, hanging out with your family. So enjoy that free time at home as well as keep up with your studies. So anyway, here's the lesson on surface area. It is not volume. Volume is the amount of cubes to go inside of a shape. Surface area is the amount of flat squares to cover a three-dimensional shape. I'll show you what I mean. These are square inches right here. And that would be the measurement to talk about surface area or square centimeters, any square units. And the first example I have is to figure out surface area of a cube. Now, if you wanted to become a packaging engineer, you would use surface area to come up with the amount of cardboard to make this lovely cube, which holds the contents of my wedding pictures. Anyway, so each of these sides are called faces. There are 6 faces to this cube. And for a cube, every face is congruent or equal. So there's a top, bottom, left, right, front, and back, and all of them have the same amount of area, surface area, flat area. And I'm going to teach you now how to find out how much cardboard to make this box. So the surface area of this cube, since it's an 8 by 8 inch face, there were 6 faces or 6 squares altogether surrounding this gift box. One square has an area of 64 square inches. Just multiply by 6 faces, and that will give you a grand total of 384 square inches of cardboard that was used to make this box as a packaging engineer. Now in blue here is a formula. If you would like to use the formula, 6 times the side squared will give you the surface area. S stands for the side length. So 6 matching faces that are 8 by 8, the sides are 8 by 8, and that gives you the same answer of 384 square inches, just like what I did here with general reasoning. Okay, so that's for a cube. Now I'll move on to rectangular prisms. Again, I want to find the square inches to make this box. How much cardboard to make this cereal box here? By the way, this cereal box is rectangular. It's called a rectangular prism because the front and the back are parallel and opposite and congruent. Same as the left and right, they're congruent, and the top and bottom. Rectangular prism. How much cardboard to make this box? Well, let me show you the net of this box. The net is simply to cut the sides open and see all of the faces. There are 6 faces. There's a front that matched the back, a left and right side that matched, and a top and bottom that are congruent. So I just opened it up so you could see it better. This is called a net of that rectangular prism. So the front here has dimensions 7.5 by 11 1/4, and that front matches the back. The left side is 11 1/4 inches by 2 inches wide, and that left matches the right. The top part of the box is 2 inches by 7.5 inches, and that area matches the bottom area. So I'll show you now mathematically how to come up with the total amount of square inches to make this cereal box. Here's the math work. There are 6 faces, 6 rectangles to make the cereal box. Here's a little mini version of it. I've got the height of 11 1/4. This long length across is 7.5 inches, and it's just 2 inches wide to the back. So over here, I broke down in table form the 6 faces. The front matches the back of the cereal box, left matches the right, and the top matches the bottom. So I used my net to figure out that the front is 7.5 by 11.25 high, and that area is 84 and 3/8 inches, square inches. And that front face matches the back face. Again, 84 and 3/8 square inches. Now the left and the right are those little parts right here for the cereal box. That left is 2 by 11.25 high, and it matches the right side of the box. Mathematically, base times height, 22.5 inches, square inches, and 22.5 square inches here for the left and the right side. The top is 7.5 by 2, and it matches the bottom, which is 15 square inches each. When I add up all 6 face areas, the grand total is 243 and 3/4 square inches. That's how many square inches of cardboard to make that cereal box. Almost 250 square inches. Over here, there's a formula if you would choose not to make a table of information. You're really saying there's 2 of a length times height, 2 of this front and back, plus 2 of a length times width, and that would be the top and the bottoms, and then 2 of the height times the width, and that's the left and right side. Just simply replace the values for height, length, and width in for the variables L, H, and W, and compute until you have that final grand total of 243 and 3/4 square inches. You will see this formula written in your textbook as well. The breakdown is very nice to see visually on the other hand. Okay, that's surface area of a rectangular prism. Now I'm going to show you a triangular prism and how to find the area. Okay, an example in the real world is, I don't have it here with me because I can't get out to Walgreens, but the Toblerone candy bar is a triangular prism. It's got 2 triangle faces and 3 rectangles that go around it, and that cardboard makes the package for that chocolate bar made from Switzerland. Here's an example right here of a triangular prism that I created at home, and basically it looks like an old-fashioned tent. Tents have the front and the back canvas, and then the left and the right side, which are congruent, and then that bottom section that you sleep on. So basically it's a tent. Now to calculate the surface area of this particular triangular prism, I cut it apart to show you the net version. Here it is. So this cut apart looks like this. There is a left and right side, and then there was the bottom of that triangular prism. And then I have the 2 congruent triangles here with all of the dimensions. Now this information I put into a poster to show you how to add up the left rectangle with the bottom rectangle, the right rectangle, and add the 2 triangles. Here's the math example. That particular triangular prism has an equilateral triangle in the front, and it's a 10 by 10 by 10 equilateral triangle. The height of the triangle I measured was 8.5 centimeters. The base is 10 centimeters. And then how long it had been from the front to the back is 20.5 centimeters. And that's that same blue triangular prism that I just held up a few minutes ago. Now, you keep hearing me say 5 faces. There's 3 rectangles and 2 triangles. The easiest way to compute triangular prism areas is just to list them. 3 rectangles listed with 2 triangles. These rectangles are all 20.5 centimeters by 10 centimeters high. So the area is just to multiply the base and height for every rectangle, which is 205 square centimeters, 205 square centimeters, 205 square centimeters. Triangular area, you learned in 6th grade, is half base times height. Looking closely at the diagram, the base is 10 of the triangle, and the height is not 10, it's 8.5. That height is perpendicular to the base. So half of a base times height is 42.5 square centimeters. And there's two triangles that are congruent, so another 42.5 square centimeters. The grand total of the 5 faces is 700 square centimeters to make that blue triangular prism that I held up right here out of my blue poster paper. So now I don't want you to get confused that these equilateral triangles are always equilateral triangles for triangular prisms, which makes the math of the rectangles always match, because the triangle sides are always congruent, then the rectangles will match. You can also have scalene triangular prisms and isosceles triangular prisms. I'll give you one more example of an isosceles triangular prism. I do not have a real object for it, and I do not have a net version of it as well. I just drew this. So see how tall this tent is? Let's pretend it's a tent where we could stand up nice and tall. It's not an isosceles triangle, not equilateral. 10 and 10 make it isosceles, and it's just got a short bottom base of 6. Okay, now we've got here that all of those sides that point up to the top of the triangular prism like a tent are tents. It's not very wide toward the back of this tent or triangular prism. It's just 4 units back. So notice the faces, 3 rectangles again, and 2 triangles. Now the rectangles have two rectangles that are congruent. The right side is 10 by 4. You can't see the left, but it's also 10 by 4. The rectangle on the bottom, pretend you would sleep in the bottom of this tent, is smaller. It's a 6 by 4 area, just 24 square units. The triangles do match. The back and the front triangles match. Half base times height, half of 6 times 8, not 10, 8 is the height, perpendicular to the base. So I've got 2 triangular areas that are 24 square units each. Add the 3 rectangles, 2 triangles for your grand total of 152 square inches, let's say. Again, isosceles means there would be 2 rectangles that are congruent. The third rectangle is not equal to the other 2. So with a scalene triangular prism, you would have 3 different sides and 3 different rectangular areas. However, those triangular parts are always congruent. The front and the back triangles are congruent always. If this was difficult for you, go back and look at each of these examples before even attempting to read the examples in the textbook. I did my best. I hope you liked it. Please email me with any questions. I'd be happy to answer them, as well as Mrs. Phillips or Mr. Whalen. Keep doing your math and have fun doing other activities with your family. Bye.